right? And I think that would be just better to erase this, guys. All right. We can even a little bit enlarge this page, okay? Okay, so let's look at one example here. It says calculate the bending All right. So let me see here. I'm not sure. I'm gonna check the 70, the unit Kep foot or Kep inches, I'll tell you. F prime C is 3000 PSI. All right. It is normal weight concrete. N, which, well, if you remember, it was modular ratio given to be 9. It can give you the modular of elasticities and you find the N yourself, but it just gave you directly. Okay. And let's look at the cross section. The cross section is like this. It is 12 inches here. It has 3 reinforcement. (17" and 3", so totally it would be 20", right? Okay, so this 3 reinforcement on this level, 3 number 9. So grade 50 they are. Let me write it outside, it would be better, probably. All right. So talking about the reinforcement. All right. So this number 9, I'm gonna show you maybe. Let's see if this session, can I have it here? So there is a reinforcement chart for American reinforcement reinforcement bars that goes from number 3 all the way to number, if I'm not wrong, it is 18 or something. So it is a standard basically reinforcement pattern that there is like a size, a cross section, diameter are often given based on the number associated to that. So here in this problem, we are using number 9. I think this most likely this is among the that file that I shared with you in the Canvas. If you remember, that was one of the first announcements I shared with you. I showed you one file that contains a lot of tables. So it is there most likely. If it is not there, I'm going to share it with you. But anyway, so number 9 bars. So the cross sectional of number 9 bars, for example, is 1 square inches. All right. So since we have 3 number 9, so right, it means the cross section AS of your steel would be 3 times 1, right? It would be 3 square inches. You have 3 bars. All right. All right. So the first thing we want to understand is if the system will crack or not. All right. That would be our first understanding from this problem. Based on this moment in the system will crack or not. So you realize that we got to use FR, right? FR, the margin of rupture is 7.5 lambda F prime C. Okay. So if you want to do that, 7.5 lambda is equal to what? It is 1, right? Normal with concrete. The square root of F prime C is 3000. All right. So the answer to this would be 411 psi. All right. So let's also find the gross moment of inertia at this point, because we are assuming that it is not cracked yet. So if it is not cracked, you can use the moment of inertia, gross moment of inertia, say 12 inch times the total height is 20 inches to the power of 3 over 12. So it would be equal to 8,000 inch force. All right. So using this, if you remember, I said, all right, so if I want to find the corresponding, cracking moment, I can say the cracking moment times y over I, it is equal to, make it equal to your threshold FR, stress-wise, right? So from this, you can say what? You can say the cracking moment is equal to I FR over Y. Okay. So this I would be IG, right? The gross moment of inertia, because we are assuming it is not cracked yet. So if it is 8,000 times FR, which is 411 psi over Y. Y would be the half, right? This is the neutral axis. So Y would be this much, would be 10 inches, correct? Okay. So this answer, as you can see, is going to be in terms of pound inch, right? The answer would be in terms of poundage, because that's what you have used. You have used pounds and inches as a unit of length. But what you want to compare eventually would be, you're going to compare with the 70 kep foot guy, right? Okay. So let's just find the answer. Let's just go step by step. So 8,000 times 411 over 10. This would be 328,800 pound inch. So let's just change it in kep foot. So what you're gonna do, you're gonna just divide it over 12,000, right? So if you divide over 12,000, it would be 27.4 kep foot. All right. So this is your cracking moment. Your cracking moment. So what is your actual moment here? 70. As you can see, your actual moment in the system, in your structure, is 70 kiloport. All right. So what is your natural conclusion? Your cracking moment has found to be less than your actual moment. Actual moment is much higher. So it already passed this 27.4 long time ago, right? So it is cracked for sure. It's gonna crack. Okay. So it is cracked. It is cracked. Okay. Okay. So we need to use transformed moment of inertia to calculate stresses. All right. So I'm gonna now erase the writings of this calculations and then start to talk about the how to find the correct moment of inertia or the transformed moment of inertia. You can call it either way. Okay. So let me erase this one. All right. Okay. So what is my assumption? What I'm going to assume here, if I want to find a crack system, I'm going to assume let me write in terms of a note. When concrete cracks, all compression, all right, is resisted by concrete and all tension only resist by steel. So when concrete cracks, all compression, I can add here only as well. So compression only by concrete, tension only by steel. All right. So if I want to show the cross section after cracking based on this assumption, does that make sense for you if I say, all right, if this is my neutral axis? All right. So a portion on top, which is under compression, all right, is to be resisted by concrete. The bottom, all right, only a steel will resist. Okay. Okay. Now, why I'm making like this? Because I want to find the moment of inertia of this system now. Why I'm making a longer steel? This is my steel. This is the converted steel. Why? Because I want to use the modular ratio. I want to use a modular ratio. Okay. This is, and the top one is concrete under compression. Okay. So what are the dimensions I'm dealing with? So this dimension is 12 inches. So this height you do not know at this point. We are trying to find the location of neutral axis. I'm gonna show that X, okay? What about this side? So in your mind, unfortunately, I cannot ask you. I would love to ask you that anyone knows what this side would be. So if you think about it, this portion, right, would be what? Would be this whole D, if you think about it, right? So this portion is D, right? Let me just do it like this. That makes more sense probably for you. This is D, right? The whole thing is D, because that's from the top edge to this reinforcement level. So this is the reinforcement level, right? I kept it the same. So if the whole thing is D, and this is X, as I just named it, so this one would be D minus X, right? So it would be 17 minus X for this one. Okay. And the steel amount here, if you convert it, we're gonna say N multiply by the steel amount. Why N? Because the cross-sectional area of the steel, AS, needs to multiply by the modular ratio to enlarge it, to make it equivalent material-wise to concrete. This is a concept from mechanics of material, by the way. Don't be mad at me if it doesn't click. It is from mechanics of material. Two different materials, we convert them, we make them same, and then find the moment of inertia of them. So modular ratio between steel and concrete 9 times AS would be 3 square inches, 27. All right. So we have the system ready. Okay. So we want to find the neutral axis. Okay. So if you want to find the neutral axis, we would say find the neutral axis. We want to say the first moment of area in compression to be equal to first moment of area in tension. Okay, why we are having this? Because of having equivalent in the system. Equivalence in the system in a way. All right. So what we can say about it? So here we can say the area. So by writing taking the moment about neutral axis. Okay. So what would you taking a moment about neutral axis? First area moment, it is very similar to what you read in shear Q, the term Q. Remember that? How you would find the Q? You would say area, right? Which is 12x times the same distance between the centroid of the area to the axis of interest. Remember this? Times x over 2. This would be for the top, okay? Equal. So first area moment of the tension at the bottom. Again, you are dealing with the area, which is, you have found to be 9 times 3, 27, right? 27 square inches, okay? So this distance, because you are assuming it is a line, so the distance is already pretty known, right? It would be 17 minus x. Okay. So when we have this situation, when we are using the first area moment of compression and tension to be equal to, and then finding this this configuration, so we can solve this equation. Let's just solve it. We can solve this equation. Let me a little bit erase this top one here. Maybe I can erase this guy's a little bit as well. Okay. So to solve that, you're gonna write, it's gonna become 6x squared plus 27x minus 459 equal to 0. So you know how to solve these guys, right? You can say x is equal to negative b plus minus b squared minus 4ac over 2a. Okay. So if you use this, the x, make a long story short, x will be equal to 6.78 and negative 11.28. Okay, so this is unacceptable. So this is your correct x. So the x would be 6.78 inches. Okay. Now you know what is the x. So x for this one, let me erase that portion here. This one too. So x is equal to 6.78. All right. And this distance would be what? Would be 17 minus 6.78. Would be 10.22. Okay. Now for this system, you can write the correct moment of inertia. Correct. Also, both of these guys can be used to talk about the correct moment of inertia. So TR as transformed or cracked CR. Both of them are talking about the same thing in concrete. Okay. So if you want to find the moment of inertia of the system about the neutral axis, what would you say? So do you know that the moment of inertia of the top rectangle, when there is a, when you are talking about one ends of the rectangle, it's going to be BH third over 3. Remember that? So it would be BH third over 3, right, for the rectangle. For this bar at the bottom, so this bar of with the area of 27 square inches, right? And no thickness, right? Because since we are assuming there is no thickness on it, just like one layer, it's just one line basically. It's just one line, all right? So when we are right, so I'm going to use a parallel axis theorem. I'm going to say BH3 over 12 plus, all right, area d squared, parallel axis theorem for the bottom one, all right? The thing is that, well, the B, you know that the B was going to be a long line, all right? But the height, what we are assuming, almost 0, right? The height is 0. That's our assumption. It's just like one layer. It is just like one line, doesn't have any height, right? So this term would be 0. So only this term would be your moment of inertia, AD squared. All right. So let's write it. So for the rectangle on top, so let me erase this guy a little bit here. So for the rectangle, you have 12 times 6.78 to the power of 3 over 12 plus this guy. This AD squared is left, right? Because it's say already 0 plus this guy is 0, nothing about the AD squared. So what is the area? It is 27 square inches, right? 27 multiply. Now, what do you have? You have the distance would be 17 minus 6. We have found 10.22, right? AD squared. Okay. So your crack moment of inertia, or you can show it this way again as well, just to make you familiar with both of them, would be 4,067 inch force. All right. This is a crack moment of inertia. Okay. Now that we have reached this point, let's find the bending stresses. Bending stresses. Okay. So let me erase this. I don't want to erase the whole thing though. Let's just erase. Yeah, we do not need these for sure. All right. Okay, so bending stresses. So for bending stress, the allowable bending stress, let's just put it in a better way. I would say of concrete, I would say actual bending stress of concrete would be MC over I. Okay, this would be the crack one, right? Which is equal to, your bending is 70 kip foot, right? Times 12 times 1,000 to make it in pounds inches. The C, what is the C here? This is the C, right? Because it's your neutral axis. So this is C would be 6.78 inches. Crack moment of inertia, we just calculated to be 4,067 inch force. Okay, so the answer to this would be 1,400 psi. Okay. Now let's look at your steel actual stress. Okay. We can find it using this formula. Remember that NMC over I cracked. Okay. It would be equal to, so the N is number 9, correct? The moment of inertia, sorry, the apply moment, 70 kip foot, again, multiplied by 12, multiplied by 1,000 to make it kip inches. Now, the distance between the reinforcement and neutral axis would be 10.22. 4,067 inch 4. All right, it would be equal to 18,998 psi. All right. So these two These are stresses in the beam due to applied / actual moment of 70 kPa. All right. Now, so these are the actual stresses. So now we want to just simply compare these two with the limit, like what with your allowable stress. What is how much you can reach? Remember that we already talked about that, talking about the concrete to be 0.45 and it's still to be 20,000. Remember that? So I'm going to use different color. Now, these are your limits. All right. So what are the limits you have? So for FC, you have 0.45 F prime C. 0.45 times F prime C given to be 3,000 PSI. Okay. So it would be 1,350 PSI. Okay. For the steel, the limit, as we discussed, for grade 50 would be 20,000 PSI. Okay. So now, if you compare, let's just compare. So I'm going to use a highlighter to show you better comparison here. Here, all right. So if we compare actual FCT with limit FC, you have actually gone to 1,400 PSI, on which you couldn't go further than 1,350. So you're passing the limit. You're passing the limit, right? Let's look at the other one. You have reached for a steel, actually, you have reached to 18,998. Your limit was 20,000, so you're good. You're below that. All right. So 1 centimeter, write this number, just clean the page, write these two numbers. All right. So your FC actual, you have found 1,400 PSI. All right. Comparing this with your FC limit, it was 1,350 PSI. So it is more than this. Not good. Your actual is more than the limit. FS actual, you have found 18,998. Compare this with FS limit to be 20,000 less than, so your actual is less than limit. Very good. Okay. So this is the result of analysis. The 70 is not good. The moment of 70 is not good. So what is good? The question is, all right, what moment is good? So let me write this first. So moment of 70 kPa is high and not acceptable. Okay, what is the acceptable one? So this one you're good on this in this one, right? But this one needs to be fixed. So let's just work on the concrete. How can I fix the concrete? Well, the way I can fix the concrete, I can say, so I can say the moment on concrete that is allowed, let's say, it is equal, all right? So let me put it in this way, let me just, I don't want to skip any steps. All right, so the FC, it is equal to what? Moment Y over I, okay? So this is the limit, okay? So it is a certain number for me. So what I do here, I would say, and what is the number here? Here. This is the limit, right? I don't want to go past that. So I'm going to say 1350 psi. It is equal to. So the moment that is allowed, I do not know that at this point. I want to find it. All right. Times. So it is for concrete side. Don't forget, it is for concrete side. So for concrete side, you know that the Y for concrete, what was that? From the figure, it was like 7. 6.78, right? And moment of inertia needs to use a cracking one for sure. 4067. Okay. So if I solve for this, your allowable would be 67.5 kip foot. You need to basically, it's going to be pound inches, and if you change it to kip foot, it's going to be this number, right? So for 70, you weren't good, but for 67.5, you're going to be good for both scenarios. So somebody might say, all right, you change and check for concrete, you are good with this number, but it's going to be good for steel, right? For sure, it's going to be good for steel. Why is going to be good already? Because the steel was good even for the higher moment. For 70 was good already. So if it is less, that definitely is going to be still working for the steel, because, well, you're just reducing this, the moment and the stress as a result. So for sure, you're going to be good. The only problem, your critical point was a concrete one on this problem. So when I fix that, both of them are good. So this is the moment, this is the maximum moment you can reach to. All right. Thank you, everyone.